Welcome to the GlobalFoundries technical webinar, Analog Design Workshop for 22FDX 22nm FD SOI Technology. Hi, my name is Sean O'Kane from ChipEstimate.com, and we are pleased to introduce today's speakers, Timothy S. Miller, Senior Member of the Technical Staff at GlobalFoundries. Please note that this detailed workshop is presented in two parts. This part presented by Timothy Miller focuses on analog layout. Part 1, focusing on analog design, is available to view on the GlobalFoundries and ChipEstimate.com websites. For now, let's join Timothy to learn more about 22nm FD SOI analog layout.
Okay, thank you. In this part, I will be covering the analog layout best practices for our 22FDX process. I will be showing some of the advantages of using the 22FDX process as it applies to analog layout. I'll cover general layout guidelines as well as layout dependent effects, how to do layout for matching, and we'll provide some examples of layout matching test cases. We'll also cover techniques for layout area compaction, including drawing transistors under the AP-MOM devices, sharing of wells, and how to use the S3 and T3 layers. We'll also show some other layout techniques, and we will cover the use of the SXCUT layer. And finally, I will go over antenna and latch-up rules and end with a summary and conclusion. I'll be covering some of the advantages of the 22FDX analog layout. It's less sensitive to layout dependent effects such as length of oxide diffusion, oxide spacing effect, and well proximity effect, except for the PMOS length dependent effect. The PMOS is a special device in 22FDX and is sensitive to layout. We have excellent device matching, including the EG devices. We have high MOM capacitor density, and we also have high capacitor density for the MOS plus MOM for supply and regulator decoupling. As far as general layout guidelines go, we suggest adding dummy devices around critical matching devices. We recommend using uniform PC and RX spacing. You should align and overlap the dummy poly to guarantee uniform RX spacing, and use mosaic layouts when you can. This gives more uniform spacing around the transistors. Big transistor arrays or polyresistor arrays will have high RX or PC densities, and that can affect the matching. We'll cover that in a later slide, and you should look at the design manual to make sure you're adhering to the density rules. You should avoid using RX and PC for signal routing. You should be sure to have adequate well, bulk, and substrate ties, and all PC, RX, and N wells should be rectangular in shape for better matching. You should use an even number of MOS fingers for merged devices, and you should evaluate the length of oxide diffusion for MOS units in an array, especially for the PMOS. As I mentioned earlier, the PMOS is sensitive to the length of oxide diffusion, and when it is used in a headroom sensitive design or clock driver, you need to pay attention to the length of oxide diffusion. You should avoid sharing RX for MOS with different lengths, and if possible, you should connect from both ends for a lower gate resistance. I'll now go over the layout dependent effects. Some key ideas for reducing the analog area. In general, the layout dependent effects are minimal in our 22FDX process, except for the length of diffusion for the PMOS, which needs to be treated carefully. For the core PMOS, the SASB needs to be increased if we're worried about VT shift. In analog cases where you need good matching and low VT shift, a longer SASB or well-matched SASB is desirable. The layout can be compacted to the limit of the DRCs so long as you meet the limits of the PC and RX density rules. When you're matching two or more devices, you need to make sure they have the same surrounding, so the same RX and the well, to match the LDE effects as closely as possible. You always need to check the LDE effects using SPICE and Spectre simulation. The LDE model can be turned on or off using the global switch GLLES. By default, the LDE model is turned on, so GLLES is set to 1. This will help you debug your design in terms of LDE. It increases simulation time slightly. Regarding the length of oxide diffusion effect, it affects mostly the PMOS more than the NMOS in our SG devices. The length of diffusion impact on the NMOS is almost negligible. It is negligible for the 22FDX I/O devices as well, the EG going from min SASB to 2 microns. To mitigate the LOD effects for two matched devices, the default PDK assumes that there is no merged RX. However, a rectangular RX shape will help modeling accuracy, and for dummies, we suggest following the rules of the RX tuck. Common centroid ABBA layout can cancel the linear gradient, but the LOD effect favors ABAB. So we recommend using the ABAB style for length of diffusion effect. The reason behind this is fairly clear. The LOD on the case on the left will match for the A transistors to the B transistors, whereas the case on the right, the LOD will have more an effect on the A transistors than the B transistors. To minimize the LOD effects, especially for low finger count devices, the length of diffusion effects are well known and more prominent if the number of fingers are lower. To minimize this effect, the diffusion area can be extended away from the critical transistor by adding dummy transistors at both edges, especially for the SG PMOS. Dummy transistors can be used as a decoupling capacitor. When using the SG PMOS with limited number of fingers, you should note that the VT may be slightly higher than the target value. And even when you're matching the two SG PMOS devices or using a PMOS in analog, it's still better to increase SA and SB for the PMOS to have the VT at the right value so it doesn't affect your headroom. Now the SG NMOS and all the EG devices can be minimum SA, SB since they are less sensitive to the LOD effect. The oxide spacing effect is essentially the spacing between the transistors, and it is caused by the mechanical stress around the MOS, which is similar to the length of diffusion effect. SPICE and Spectre take this into account as well, and some examples of the OSE-X and OSE-Y core devices are shown in the table. Picture on the left shows where OSE-X is the space in the X direction between the transistors, and OSE-Y is the space in the Y direction. When trying to mitigate the OSE effects, a standalone device should have dummy RX to have a well-predicted VT. The recommended dummy RX spacing to the main device, if it's alone, can be drawn with minimum design rules. You should refer to the design manual for the rules regarding RX and RX tuck. When matching several devices, the OSE distance needs to be the same on all of them. And for layout compaction, you can use the minimum OSE-X and OSE-Y set by the design rule checker. Well proximity effect is similar to OSE. it is, for the SU devices, it's really negligible. This is because the process is an SOI process, so the distance to the well does not make a big impact. The same applies to the AG devices, mainly when the width is large, 1 micron or above. But you do need to make sure that the well spacing of any device is the same for the devices that need to be matched. I'll now show some examples of how to do layout for best matching. The key idea for reducing analog area is for matching. The 22FDX has good device matching even for the high voltage devices like the EG. And the end result of this is good area savings in applications like data converters, analog baseband amplifiers, analog filters, and biasing circuits and current mirrors. Here's several examples of transistor matching and the basic terminology regarding transistor matching. So the case in the upper left shows a symmetrical layout where there is a line of symmetry about the center. The top center example shows interdigitated layout where there is it's using an AABB AABB type alignment. The top right shows a cross-coupled layout. Bottom left shows your common centroid with interdigitated layout. The bottom center is interdigitated layout going ABAB. And the bottom right is an example of your cross-coupled layout. When you're trying to use matched pairs for differential signals, you need to be careful about the signal routing and the parasitic mismatch. The example on the top shows unsymmetrical parasitic layout and loading for the transistors. You can see that the load on signal for A is less than the load on the signal for B. You need to minimize and balance the routing resistance and the ground for the NMOS bias mirror, the source, the PMOS and NMOS for the differential pairs for matching devices. You should always tap at the line of symmetry. So the example in the bottom left is showing an example of how not to tap, where the resistance would not be balanced. The ideal connection is shown in the bottom right, where the resistance on the left and the right are balanced. When you're trying to array matched devices, a current source or a current steering DAC is shown in this example. You should use identical unit cells as a building block for matched devices, which includes identically sized transistors, critical routing, dummy fill, and well and substrate ties. You should place the unit cells equally or butting with a common boundary, and you should place them with the same orientation. You also should ensure that every matched unit cell sees a uniform density gradient, especially for poly and diffusion, as that will impact the matching. You need to avoid having abrupt density changes, especially near the edges of the array. You can improve the matching by surrounding the array with rows and columns of dummy cells, depending on the matching requirements. And if dummy fill is necessary inside the array, the dummy structure can be added manually in the unit cell itself so that they are identical across the array. This would be ideal. If it's a large array, you can use gradient cancellation techniques that can be found in literature. If you're doing an array of matched devices, in this example a current mirror or current source, typically the matching requirement is relatively less stringent compared to a current steering DAC. Using unit cell layout to scale to the current mirror ratio is a better choice compared to just using numbers of fingers. For current mirrors with large ratios, commonly used matching techniques such as in common centroid interdigitation of unit cells can be used as applicable. Now typically a current mirror or a current steering DAC area might have high density in poly and diffusion, So you need to make sure that the densities are within the requirement of the design rules. You should refer to the density rules section in the design manual. And finally, you need to make sure the left and right cells, in this case D1 and D2, have an RX or a dummy or another device to satisfy the OSE X matching. Regarding resistor matching, the example on the left is the technique that you should follow. You should have an interdigitated configuration with an equal structure with suitable dimensions of W and L. Dummy patterns are optional but would make for better matching. You can see the case on the left. We've connected the resistors using metal and interdigitated AB, BA, AB, BA. The case on the right is what to avoid doing. You should not have serpentine resistors. You should keep the devices away from power sources. I'll now cover techniques for layout area compaction. One of the nice things about the 22FDX is we allow this combination of capacitor which increases the capacitance density and saves area. So usually a large area of analog and RF SOCs are placed with decoupling capacitors for power supply and on-chip regulation. Using high-density decoupling caps will save a lot of area. Usually decoupling capacitors need to be high Q, so have low series resistance. The following two slides show how to increase the density of the MOS capacitors by adding an AP-MOM capacitor on top of the MOS capacitor. The first option uses larger capacitor unit cells and has a higher density but lower Q. The second option has smaller capacitor unit which provides better Q but lower density. So here's the first example where we've combined an EGN cap with an AP-MOM 3.3 volt. Now only C1 through C3 metal layers for DRC and LVS are used. You can use more metal if it's available, which will give even higher density. The case on the right is the combo high Q EGN cap plus the AP-MOM 3.3 volt. And once again, this only shows C1 through C3, but you can use more metal if it's available. In this case, the EGN cap are broken into smaller units. And here's a great representation of how much area gets saved. The motivation is we see a 2x area savings and minimize critical routing in the programmable capacitor, which is the AP-MOM plus the transistor switch, for an analog filter and an RF receiver front end. The case on the left shows a non-compact version where the AP-MOM and the switch do not overlap. And you can see the end result area is 65 by 50 microns and is spaced AP-MOM switch, AP-MOM switch, AP-MOM. The case on the right is the same circuitry, but we've moved the switch circuitry under the AP-MOM, and the end result is a compacted version that is only 50 by 20 microns. Another technique for layout compaction in 22FDX is sharing of wells. The cross-section shown on the right shows where an SLVT N FET is placed next to an SLVT P FET. The SLVT P FET in this case wants to have an isolated P well. We can draw T3 or S3, which is essentially deep N well, under the SLVT P FET, creating an isolated P well. The N well that helps isolate that is on the left side part of the N well of the SLVT N FET. So you can share deep N wells for flipped well N FETs and P FETs. This reduces the layout area. It allows you to apply a back gate bias separately. It also applies for low power and high speed buffers. There are some cautions, however. The N well potential needs to be greater than or equal to 0 volts to avoid forward biasing of the diode. The P well potential needs to be less than or equal to the N well potential, and we suggest putting LVS diodes inside the schematic to catch forward bias diode conditions during simulation. Continuing on regarding the sharing wells, here's an example of sharing a deep N well for backgate biased inverter based buffer. Once again, the cross-section shows the deep N well drawn under the isolated P well of the SLVT PFET and using the N well under the SLVT NFET as part of the isolation of that P well. Bottom drawing shows a top-down view of the layout of the structure above, with a P ring on the outside, an N ring which is connecting to the N well on the inside, and the deep N well, which is the T3 or S3 layer drawn slightly inside that. The end result is the white area is the isolated P well for the SLVT PFET. The use of the S3 and T3 layer is for creating the deep N well under the isolated P well. The S3 and T3 layers are both the same mask layer, however the design rules for the S3 layer are less restrictive than the rules for the T3 layer. So using S3 will allow the designer to have a more compact layout. Now the S3 is intended to be used for biasing purposes, while T3 should be used for noise and isolation purposes. You need to use caution when using the T3 and S3 layers under multiple wells, because this will short all the N wells together and will be flagged by LVS. So for isolated well purposes, we suggest using the 5 and 6 terminal symbols, for example the NFET TW and the associated P cells. Regarding other techniques, via placements to improve the resistance on the 20 and 24 nanometer devices. The problem that you may face is that at the very small device sizes, the current device layout typically requires as much metal and stacking as possible. In the short channel devices, this creates a set of design rule via spacing violations, because the vias on the source spacing to the vias on the drain will violate the minimum rule if they are placed at the same y coordinate. The solution, as shown in figure 1, is to shift the vias on the source or the drain so that they are offset from in the y direction from the vias on the source. So for via 1, making a spacing of 116 nanometers and placing them as shown. Figure 2 is similar for the AY layer, and figure 3 is the A1 through A5 vias. Regarding double patterning, so the 22FDX process uses a technique for metallization called double patterning. Because the spacings and geometries are so small, we're unable to put the M1 data on one mask. Instead, we split it into two separate masks referred to as E1 and E2, exposure 1 and exposure 2. The process of generating the two masks is called decomposing or coloring. The designer draws the shapes on one drawn layer, for example metal 1, and then we run a program which decomposes it into two masks, metal 1 and or M1 exposure 1 and M1 exposure 2. The decomposition can be done manually or with a design rule deck. The decomposition can be done at the cell or the chip level. The basic requirement is that the design should be decomposable to avoid an odd cycle violation. An odd cycle violation is a set of 3 or more metal patterns which can't be decomposed because the coloring would lead to a spacing violation on one of the masks. So the solution to that problem is to increase the separation in at least one of the spaces in order to allow for automatic decomposition. So the layout needs to be design rule clean as well as odd cycle clean. I'll now go over the usage of the SXCUT layer. Now, the SXCUT layer is a CAD layer used for defining 2 or more regions of substrate for LVS purposes. that are electrically connected but have different names in the schematic. So for example, it can be used to split grounds for analog and digital, such as VSSA and VSSD for LVS purposes. You need to use this layer carefully and only when it's absolutely necessary. The reason is because it's only a tool for LVS purposes, but in silicon it is not separating the substrate. It's only one substrate, and they will be connected together. Some SXCUT usage guidelines. If the SXCUT layer has to be used, you should make sure that the layout does not have any SXCUT layers overlapping the S3 or T3 layers. The reason is because that can hide some real shorts in the layout during LVS. Overlapping of SXCUT and the S3 or T3 layers is usually flagged in the ERC check, but in some cases it might not get flagged. If the SXCUT layer is used in the design, we strongly recommend that the LVS methodology described in the next slide be performed before tape out. And please note that ERC is not on by default, but we strongly recommend that you run ERC before taping out. So the recommendation of an additional LVS check. If you've used SXCUT, we recommend an additional top-level LVS check to confirm there are no hidden shorts that are unexpected. What the user can do is on the schematic side instantiate a top-level symbol and short together all of the P substrate pins. And then on the layout side, you can remove the SXCUT layer or simply not stream it out and instantiate the top-level block of the layout and short all the pins together to the P substrate. Then LVS between the schematic and the layout should match. If it doesn't match, then you've found an error and you need to resolve it. Antenna and latch-up rules are similar in FDX as they are in bulk. So the mechanism of an antenna damage is induced in the gate oxide due to plasma processing, including poly, the interlayer dielectric, contacts via, and metal. So due to the fact that it's not bulk, there's no SD diode to substrate. Unfortunately, the source and drains are still susceptible, so antenna protection is needed on all of the device terminals. These are covered in the design rules. A maximum ratio is defined for the metal area or the via area to the poly gate area. Now 22FDX has an isolated source and drain. The metal connected to the source drain is subject to the antenna rules as well. The VV via, which is between the top copper and aluminum, has a very stringent ratio. This is something that needs to be paid attention to. The EG devices, which are the I/O devices, and the SG devices, which are usually the core devices, have different ratios due to the different oxide thicknesses. The EG rule is more stringent. How to fix the antenna rule violations? There are a few techniques. The first is to reduce the metal or via area until the maximum ratio is met. Another technique is to break the metal and go to a higher metal jumper, which will reduce the large area over the lower layer metal to the gate. The third technique is to use an antenna diode, which is a reverse bias diode, to add more discharge path. Or you can add a well tie or substrate tie, which is also the antenna diode area. Now most of the time the ESD diodes help fix the antenna violations at the I/O, and antenna violations on nets with negative voltage swing need to be fixed using back-to-back diodes. The only negative impact is it adds some design time, and the diodes impact the parasitics and the linearity, so you should use caution and balance them when you can. Here's a list of the most common antenna equations and ratios, with the metal to gate with a ratio of 2000. So here's an example of a solution. The problem is shown in the drawing on the top right, where the ratio between the C1 layer and the gate is too high. One solution, shown as solution 2 in the middle on the right is to break the C1 layer and go up to C2 before going back down to C1. The only metal used in the ratio would be the C1 on the left. And the other solution, shown as solution 1 in the bottom right, is to use a tie-down diode, which eliminates the ratio. Now, you need to correct the antenna as much as possible at the lower level, but remember, sometimes there might be a diode to mitigate the antenna at the next level up. When trying to attach an antenna diode for negative voltage, you need to use the back-to-back diodes. You can implement these in several ways. You can use a P-cell if it's available. There's a version with floating N-well, FLT-NW, and that is used to allow floating N-well during DRC check, and hence it doesn't require the N-well tie or the guard ring, which helps minimize the area. Now, the layer purpose pair LVS1 drawing 8 is added to identify the parasitic N-well to P-substrate diode, and the diode NWX LVS device is used to match the schematic during LVS check. You should refer to the design manual for the most recent rules. For the antenna diode to protect the negative voltage, according to the design manual, when you're extending the boundary of the floating N-well layer, the FLT-NW layer, over the boundary of the N-well, that can reduce the sidewall parasitic capacitance of the N-well to the substrate well junction. And this extended area is to block the P-sub implant from the increased resistance. Regarding ESD and Latch Up, some basic general guidelines are provided. There are fewer SD diode junctions in 22FDX, and that reduces the number of latch-out prone layouts. The antenna diodes can be injection points for latch-up, and only required size to pass antenna rules should be used. The design rule checks identified latch-up based on pad tagging, and nets connected to the pad should be labeled in the ESD layers. We have a few ESD label keywords, which are shown in the table at the bottom, and each pad should have one of these labels. I'll now summarize. We've provided an overview of the analog-related FD SOI characteristics. We've highlighted selected advantages for analog circuits. We've shown examples of circuits that do not use backgate bias, as well as the use of backgate tied to front gate, forward and reverse backgate biases with examples, and provided analog layout best practices. Thank you.
Thank you for joining us for part 2 of the webinar, Analog Design Workshop for 22FDX 22nm FD SOI Technology. If you have any questions, please email them to marketing@globalfoundries.com or contact your local GlobalFoundries office. In case you missed part 1 focusing on analog design, it is available to view on the GlobalFoundries and ChipEstimate.com websites. Also, more information about FD SOI, FinFET, ASIC, RF, and other technologies can be found at globalfoundries.com.